Hi, and welcome to this tutorial. Today we're going to go over quickly how to run omeClust. omeClust is a command line tool that allows you to, if you have a distance matrix of omics features, maybe you have metabolomics data, metagenomics data, transcriptomics data, any kind of omics data for which you're able to calculate the distance between each pair of samples in your data set. It allows you to generate clusters of those data and also figure out how or which metadata variables of interest best explain those clusters in your data set. And when I talk about clustering, what I mean is that if you have some samples for which you've collected some data and you plot those samples in some sort of ordination plot, you might see the emergence of different groups of points, right? So it looks like, to the human eye, it looks like these are two different clusters. This cluster is, these samples are very tightly put together, and these samples are belong to a separate cluster, although maybe they're not so tightly put together. But perhaps there's some metadata that explains the formation of these clusters. Maybe all of these samples came from a particular body site. Maybe all of these samples are from diseased individuals or from healthy individuals, and these are from diseased individuals or from a different body type, site, etc. So I mentioned omeClust is a command line tool. Here I'm on the command line. In this case, I'm in a Unix environment. If I show you the files that I have here, I have two scripts. I won't go over those too much. Let me maybe just show you this Prereqs one. This is a script that I've already run, and it's going to create an environment where we're going to install omeClust. omeClust has a few prerequisites, which include Python, Matplotlib, NumPy, and Pandas. So those are going to be the packages that you need before you're able to install this. And I also have another script that will allow me to fetch the data. This data is available on GitHub, so you could either fetch it directly with a wget command like I'm doing here, or you could download it on your personal computer and then maybe transfer it to a high-performance computing cluster, or if you just want to run it locally, that's fine too. I've already run this prereq script, so I've installed my prerequisites, and if I go ahead and do bash get data, it'll go ahead and fetch that data for me, and these links will be available in the description of the video so you can get the data as well. If I show you what I have, now I have a distance matrix, and I also have my metadata here. If we look at the distance matrix very quickly, and I'll go ahead and remove the line breaks here, you can see that these are measures of distance between samples, between each pair of samples. And then if I show you my metadata, I have some information about the sex of these particular patients, their age, and then we also have a designation as to which cluster they truly belong to. This is probably something you don't have with your data, but this is synthetic data, so we do know to which cluster these samples truly belong to. Okay, so I have omeClust successfully installed. We can check that by simply running the omeClust-h command. It might take a second to print this out, but it's going to print out for us all of the different options that we have with omeClust. So let's give it just a second. And there we go. It's printed out some of this information here. Some of the most critical options are your input and your output. You can also specify similarity, which has a few different metrics, including Spearman, NMI, etc. You can put in your metadata, the estimated number of clusters. There's some other things here that we won't get into. All right, now that we've installed omeClust, we kind of know how it runs. Let's go ahead and run it. So we're going to invoke it with omeClust. I'm going to do -I and give it my distance matrix. I'm going to do -- metadata, and I'm going to give it my metadata file. I need an out folder, so I'm going to call this omeClust_out. I'm going to give it a linkage complete parameter. This is kind of optional, and then I'm also going to do resolution. I'm going to say medium. You can choose from low, medium, or high, so let's give it a medium resolution, and then I'm going to tell it to plot the results, and then I'm going to press enter, and after that I'll show you what the results look like. Alright, so I've transferred the output folder to my local computer so that I can look at it. It's going to print out some of these text files that have the distance matrix that you put in. It's going to have the cluster membership. It's going to discretize your metadata for you, tell you what cluster labels your clusters have. But the things I'm most interested in is perhaps this dendrogram, for example. Let's take a look at this. This will show a dendrogram of how our data looks like. So if you kind of plot it in sort of a heat map, it might just take a second to open. But you can see it looks like 4 clusters emerged here. where the columns and rows are our samples, and then the darker color mean that these are closer together. So you can kind of see 4 dark squares indicating the 4 clusters. That's the dendrogram very briefly. It also creates a number of visualizations based on different ordination methods. I'm going to go ahead and show you just this t-SNE plot here because I think it very nicely shows how our data have segregated out into clusters. And you can very clearly see that there are 4 clusters that emerge. Cluster 1 is this red, cluster 2 is yellow, cluster 3 is light blue, and cluster 4 is dark blue. And then you can see that this overlaps well with the ground truth. This is synthetic data, so we kind of knew what clusters these would fall into, but perhaps this could be, your data could be shaped perhaps by the body site where it was collected, the disease state, maybe it's by some sort of treatment that the samples were given, etc. And so we can see here that all of our samples which truly belong to cluster 4 were correctly put together. All of the circles are in a cluster together. All of the downward facing triangles are in a cluster together. All the squares are together. And it looks like all of the upward facing triangles are together. So that's just kind of an overview of how you run omeClust, what the output results look like. There's more to dive into in the publication and in the GitHub, which I'll put in the comments. But as a very brief overview of how to run it, that's what I wanted to let you know today. So thanks for watching.